Okay, so I already talked about this last time, but I'll hit it again. Strings are what we call immutable. Once the string exists, you can't change anything about that string. But we made sure to put an emphasis on the difference between the variable and the thing itself. So I can change what the string is that the variable has, but by doing so, I'm making a new string that's then taking the place of the old one. The original string is left alone unchanged. So I can change what the variable's using, or what value the variable has, but I can't change anything about the string itself. I can't go in and change a letter of the string. I can't. So we can access individual characters from the string, but I can't do something like this. I can't go and try to set it. Because once the string exists, that's it. You can't change it. If you really did want a string like here, if you really wanted to replace a particular letter, so I wanted to go in and change the comma to an exclamation point. If I really wanted to do that, I can't. But what I could do is make a new string based on the information in the old string and make the changes there upon creation. Any questions about that? Because it's a little funny, but it's the way it is. Once the string exists, that's it. You can't change anything about that string. We can make a new string based on the old string, but we can't actually change anything about the original string. It's immutable. Yes?
Does that colon just mean like print everything up to the fifth entry?
This is that slicing thing we looked about. It means, depending on how you use it, this means start at the beginning and go all the way up to, but exclude index 5. So that would be 0, 1, 2, 3, 4. So it would then say, okay, give me those 4 letters, or 5 letters, H-E-L-L-O. Then I say, okay, then concatenate that with an exclamation point, and then give me the 6th to the end. This is just string slicing. It's just it's a fancy way to do it. Yes?
It kind of has something to do with this. If you were to want to use this but with integer, not a string, let's say if you wanted to do some calculations but then you wanted to use like this type of function, is it only strings that you can use? Like
I'm not quite sure what you mean.
Okay, so let's say if there was like an input and it was like an integer.
Okay, so I've got like sum var equals 66.
Yeah.
Okay.
And then you wanted to use this function, like how you're doing it with like those brackets, but with that, would you have to convert that to a string to be able to use it?
Oh, to be able to like print, yes, you cannot concatenate a string and an integer. You can concatenate 2 strings and you can convert an integer to a string. Yes, good catch. There are other ways to do it, like there was that weird squiggly bracket thing we did, the F strings. All right. Okay. Linear search. So, linear search is, you may remember me saying, I think it was yesterday, maybe it was Tuesday, soon we're going to hit our first real general purpose algorithm. Of course, that's kind of a ridiculous statement for me to say. Everything we've done so far is an algorithm, and maybe some of those things are fairly general. But this is a very common, important thing you're going to be doing a lot in programming. Linear search. You've got a collection of things, and I want to see if a given thing is in that collection of things. Assignment 1 is using a linear search. But, you know, you're not just checking if something exists, you're looking at each individual Starbucks location, and then you're checking, well, is it in the area I care about? It's a linear search. Linear searches are very common, and it's arguably your first, like, real algorithm that we can spend some time thinking about how it works. Because a lot of computer science isn't just, here's the code. It's about taking this moment to think about what the algorithm is doing and how much work it's going to have to do and whatnot. That's something we're going to learn a lot about later, but we can start talking about these things now with this algorithm. So linear search. Searching through some collection of elements to see if something exists is a very common problem. It's something you've done in real life many times. How many of you have ever needed to go through a pile of something to find something? Obviously, right? Of course you have. Now, when you did it, you did follow some algorithm. You just weren't thinking about Python when doing it. You were following a set of instructions, though. Who here has ever had, like, a stack of assignments and you need to go find yours? Something like that? Okay. Who wants to tell me the step-by-step process they took to find theirs?
Okay, so I started at the bottom of the pile because it was sorted by last name.
Oh, okay.
And it was easier because my last name starts with an R.
All right.
And then I strictly looked at the last names to find where the last name started with an R, and then I went through and found it till my name was there.
Okay. But can someone try to take that idea of searching that stack of assignments and try to even break it down into more explicit, simpler steps? Yeah.
You look at the assignment, see if it has your name. If it has your name, you take it, and if it doesn't, you go to the next one.
That's kind of how I would think about it. Who here is thinking, they hear that and go like, yeah, that's basically it. You start at the top. I mean, you had a fancy search because you knew it was sorted and you could exploit information about that you knew about the information, the data. But in general, it's going to be, all right, you start at the top. Is this the thing I'm looking for? Yes or no? If it is, great. If not, go to the next. Is this the thing I'm looking for? If it is, great. If not, go to the next. So on and so on and so on. But that's just a linear search. And it's kind of funny to start thinking about these, searching a pile for something. Sure, it might feel like a trivial problem you're solving, but you had to come up with a series of steps in your head that you were going to follow to solve that problem. You did that. Now it's an exercise of, well, can you take that same idea, but turn it into code? Because it's going to be the same algorithm, except your fancy search because you cheated. But we'll learn about what do you do if the information's sorted later. Because if you do know the information's sorted, there's really interesting tricks. Kind of what you were doing, but we'll get back to that. So it's an exercise of taking what you know how to do in real life and turning it into code. So I'm going to give you a chance to try to figure this out. You're going to write a function called character is in. Okay? I'm going to give you a couple minutes for this one because it's a doozy. Character is in. It takes a needle and a haystack. Needle is the thing I'm looking for. Haystack is the collection I'm going for. In our particular example, needle will be an individual character. Like, for example, the letter A. And the haystack would be the string hello. And I want to know, is A in that string? So what does it say? Okay, searches for the specific character needle within a string haystack. If it exists within the string, return true and false otherwise. When you finish, run these tests to see if you're right. So I'm putting you on the spot. You got to write a sophisticated algorithm that we just talked about what it could be like in real life. But you got to write a sophisticated algorithm to do a linear search. I'm putting you on the spot, so I'm going to give you a couple minutes for this. And we'll see if you can get it working. And do remember with the for loop here, this particular would print each character out. So this would be each individual character starting at the beginning, going to the end. So just this style of for loop might be really handy for you. Excuse me. By the way, I need to take a moment. We need to congratulate someone in the room for submitting the first pull request. You, right? Was it you?
Me?
Yeah.
I did, yeah.
You did. All right. Well, you have the first pull request in the class that has been accepted and already integrated in the content. The word "sill" has been changed to "will" because it was a typo. Is anyone done now? The character is in. Anyone feel like they'll be done if they had like just a couple more minutes? I'll give you a couple more minutes. How many people are done now? Not a lot of people. Are there people that are done but the tests are failing? Interesting. So the tests that are failing, I'm curious, are they all passing except the last test? Raise your hand if your function passes all tests except the last one. Oh, all right, never mind. Should I give you a couple more minutes or do you want me to just carry on? Raise your hand if you want to just go. Okay, I'll go. Before I show you a solution, I'm going to show you this solution. And it's not correct. And it is broken in a very severe way. If I go, I'm going to take my cert tests. But of course this is broken, so I'm just going to change this name to just characters in because I don't know it's broken. So if I hit run, oh my gosh, it even fails at the first test. I thought for sure. Yeah, this one's broken. Did anyone fail like this? Even on the first one? Yeah. Let's see if I can make a quick little change here. Let me get rid of count. I'm going to turn it to a for loop. See if the functionality changes at all. Yeah, so this one breaks. But you know what? When the test fails, maybe we don't like that test. So let's see what happens now. Okay, well they all pass except the last one. Which is interesting. Because, well, this character here, this just open close quote immediately is what we would call a null character. It's nothing. And I'm checking if nothing is in there while nothing is not in there because it's, you know, it's something. It's a string that says hello. Then I check is A in there. And I know, well, there is no A in hello, and so the test passed for A not being there. H worked just fine because H is in there. But the O fails, which it shouldn't because O is definitely in the string hello. But why is it broken? Well, the way to answer this question is, what does the code say? That's always the answer. What does the code say? So let's see what happens with the A example first. I give it A, char is A, string is hello. For each character in string, I say, okay, get the H is current H equal to the character I'm looking for, A. Is it?
False.
False. Okay, so then we return false makes sense. So that gave us the correct solution. Let's look for H. So I go through char is H, string is hello. I get the first character from the string, which is H. If current, which is H, equals char, which is H, well, when that's true, return true, because we found it, right? So far, so good. Okay, let's see what happens. O. So char is O, string is hello, current is H. I compare current, which is H, with the character O. Is that statement true? False. So we immediately come down and return false. Which is a problem, right? Because I shouldn't return false yet. Because I don't know. All I did was look at the first character. So let's take a moment and go back to what the underlying idea is. So this is searching a string. We can do a linear search on any collection like this, like a list of locations. This is obviously a much more general purpose algorithm, just strings. But it's important to note we can confirm that the thing I'm looking for exists within that collection the moment I find it. Right? So, for example, I have a sequence of things, right? And it's just some sequence. And I'm looking for X, whatever X is, it doesn't matter. Before I start looking at the collection, I don't know what's in there, right? I know the collection exists and it's got some data in it, but that's why I've represented it as a bunch of question marks, because I don't know what's in there yet until I start looking at it. So, let's say I look at the first thing and it's an X. Great. I found what I'm looking for. Do I care about anything else in that list? No. False. No, because I already found it. No sense to keep looking for the thing I'm looking for if I've already found it, right? But the trouble here is, let's say I'm looking for y. Let me scroll down a titch. If I'm looking for y, can I make a conclusion after looking at the first thing? Can I conclude if y is in that list or not? False. Well, why not? It almost seems like a stupid question, but try to explain why I can't conclude that it's not on the list by only looking at one thing.
You just have to check the whole list.
Yeah, I gotta check the whole list. I cannot confirm if something is not there until I've looked at everything. So the moment I find the thing I'm looking for, I can conclude that the thing is there. But I cannot conclude that the thing is not there until I've exhausted everything that is there. In this example, it just so happened that the tests worked, right? Because, well, okay, A. But with the way it's written, I'm just checking the first letter. If it's the thing I'm looking for, return true, otherwise return false. Because remember, as soon as a function sees return, it immediately stops. This function effectively only ever compares the first letter in the string with the thing I'm looking for. If the first letter is the thing I'm looking for, it's great. If it's not, false. So it just so happened that this test passed. Same with this test. But it just so happened this test passed by dumb luck. It just so happened that this test passed by dumb luck. Because I happened to be looking for the first thing, which the broken function was doing. It wasn't until I had more in-depth tests where I discovered there was a problem. So we got to be very rigorous with our tests. You can't just test two cases. You got to try to catch all possible cases. So here I checked empty, something that's not there, something that's there, something that's there, but somewhere that's not the beginning. It only failed on this test. It would, here, quiz time. Will it pass or fail this test? Fail. Why? Well, because it's only ever going to check H. Is H E? No? All right, didn't find it. So as soon as we find the thing we're looking for, we know it's there. If we look at everything and never find the thing I'm looking for, only until I'm looked at everything can I conclude it's not there. Imagine I have a series of 100 question marks, and I've looked at everything. I've looked at all 99 things, and I have one last question mark left. And I haven't found y. Can I conclude y is or is not in the list? No. Because there's still one more thing I have to look at. If you had a pile of exams and you were looking for your exam in the pile, if you got to the last one but didn't look at it and never found yours, would you conclude that, well, yours must therefore not be there? No, that's a stupid thing to say, right? Of course not. You got to look at them all. But you can see that relationship with reality and how you're executing that algorithm in your head in real life and the algorithm here. The broken example has the issue of, if I find it, return true, otherwise return false. No, I can't conclude that the thing is not there until I've looked at everything. Until this loop is done, I cannot make any conclusions. But if I ever finish that loop, because the way it's written, in the loop, if I ever find the thing I'm looking for, I return and the function ends. So if the thing exists, the function will end before the loop ever really ends. But if the loop ever ends, I know the thing must not have been there, because if it was, line 3 and 4, that if would have tripped and we would have returned, meaning the function stops. If it ever gets to the end of that for loop, that means I have therefore looked at everything in that string in this example. Therefore, if I got here and I looked at everything, I can finally conclude the thing is not there. So this is the way to do it. And the first example I showed you is a common mistake new programmers make when they have to write the linear search. Oh, if you find it, return true, otherwise return false. When can you return false? We got to be careful about that. Let's run the test to make sure they pass. Looks good. This return is in this if. This return is outside the for loop. Kind of neat. I think this is cool. So let me ask you. Let's say I had a string with 10 letters in it. And how many letters do I need to look at in order to guarantee that something is not in there? 10, right? The string has 10 letters. I've got to do like 10 units of work. I've got to put my finger on the 10 letters. What if the string was size 20? 20. What if it's size 40? 40. Exactly, right? What if it's size n, where n is some arbitrary value? How many things would I have to look at? All of them. All n. The point I'm making is the size of the input to that function, the length of that string, has an effect on the amount of work your function needs to do. If I double the size of the input, if I doubled the length of the string, I would double the amount of work your computer has to do. Seems reasonable, right? This is an example of what programmers, computer scientists call a linear time algorithm. It's just a fancy way of saying if you double the input size, you're doubling the amount of work that's done. The amount of work you have to do is linearly proportional to the size of the input. And linearly just means like, well, if you double it, you double it. You triple it, you triple it. We will eventually look at things that are quadratic, where if you double the size of the input, you've actually done a lot more than doubling the size of the work. It scales at like an n squared. There are things that are less than n. There are things that are more than n, and so on. But a lot of the code we've done so far is what we call constant time. Meaning the amount of time it takes is independent of really anything else. Like think of like the car payment thing, right? You hit run, it's going to take the same amount of time to run. If I had a linear search and I was looking at 10 things versus a billion things, which one's going to take longer? The one you're looking for a billion. It's intuitive, but this is a linear time algorithm. You double the size of the input, you're doubling the amount of work the computer has to do. Which makes sense in real life too. If I give you a stack of exams this big, or a stack of exams this big, which one's going to take longer to look through? This one, right? Because it's bigger. Let's say it's about twice as big. How much longer will it take you to go through it? About twice as much, right? Yeah. So there we go. Okay, so here is a working character is in. I want you now to write a function, character is at, that doesn't return true, false. What it does is it returns the index of that character if you found it, and And if you don't find it, you just return -1, right? Because we need this function to return a number, and we'll use this -1 as a special value to be like, well, if I ever call this function, I see -1, I know the thing's not there, because there is no -1 index. I mean, there are a bunch of ways one can do this. You might find a while loop easier instead of a for loop in this case, but you can do it with for loops. There's a bunch of ways you can do it. Raise your hand if you're done. Raise your hand if you'll be done if you're just one more minute. I'll give you a minute. Yeah, cool. Okay, here's a solution using a while loop. I've got the standard while loop structure there. When doing something, you gotta like count for. So I've got the counter, I've got my condition in the while loop, and I'm incrementing counter. It's your fairly typical setup. Now you'll notice I'm checking if it's less than the length of the haystack. Raise your hand if you had no idea you could do this. A couple people. More than a couple people. Well, you can. You can get the length of a string with like that. Then I'm saying, well, if haystack at index counter, so it'll start at 0, is equal to the needle, the thing I'm looking for, I return counter, because counter will be the index. If this if statement doesn't get tripped, fine, just increment counter to 1. Is 1 less than the length of the haystack, and so on, and so on, and so on. And then if we ever finish that loop, we return -1. Did anyone in here do it with a for loop? Did you use range? Yeah. Yeah, cool. Did anyone use what I use there, enumerate? One person? We'll talk about enumerate later. So yeah, this was here. Did anyone start with this and then hack it to make it work? No? All right, that's fine. Just curious. So there, that's a slightly modified linear search. Don't just tell me if it's there, tell me where it is. So now I'm going to just spam some facts about strings at you. You can use double or single quotes when creating them. Both are fine. You can concatenate strings with plus. You've already seen that. You can multiply a string to have it repeat itself some number of times if you'd like. You can convert an int to a string if you want by wrapping it in stir. The string open and close is a string. It's just, we call it an empty string, which is kind of weird, right? Because the length of the string is 0, but it's still a string. It's kind of funny. There are special characters. There are a lot more than these two, but /n/t. Anyone know what those do? /n means, let me show you. Actually, well, here, this shows you an example. Okay. Okay, I have this /n in here. Let me put it this way. What if I wanted a string, but I wanted it to print hello and world on 2 separate lines, but I'm only allowed to have one print? How would I do that? What do I press on my keyboard to say, like, new line? Well, you hit enter, but then that's going to be a problem because Python thinks, well, you just wanted a new line. So how do I put a new line in there? Well, we use this special /n for new line. And it means just, it's a new line. Yes?
What if you want a string that has /n?
If you really want that in there, you do //n, I think. Yes. So you escape, the slash is like the escape character. So if you need that, you need to like escape the escape character, and then you have it. One thing to note about single versus double quotes. One, if you have double quotes, you can put quotes within your string, like that. But if you're using single quotes out here, you got a problem. But you can solve it by doing this, but why not just go with the double quotes? I'm going to recommend you use just double quotes in general, because other programming languages have double quotes is string almost universally. Single quotes is something a little different. It's an individual character. So FYI, I recommend using double quotes, but you don't have to. /t It's the same idea with new line, but with the tab. That's all. Ascii table. So every character is a number, whether you like it or not. And every number can be, well, no, that's not really true, but every character is actually a number, and you can get it by asking what the ordinal is of it. A happens to be the number 97, and the number 97, like the integer 97, is also the letter A, which is weird, but it is. If I were to take the character of 65, seriously, let's see what happens here. I convert the integer 65 to a character and I print it out. And I get the letter A, capital letter A, which is kind of weird, right? Well, there's a reason for that, which we won't get into right now. But this is what we call an Ascii table, where you can see like, well, let's see, capital A is 65, lowercase a is 97, and so on. The reason that each character and integers, like how there's that weird overlap between the two, is because, remember yesterday, or 2 days ago, I was talking about how like things fit nicely in here, the number of zeros and ones I have? Well, it turns out the sequence of zeros and ones that means 97 is the exact same sequence of zeros and ones that means lowercase a. The same 0 and 1. Okay, thanks for pop-up. No, and bye. So 11000001 means 97 if I go in it looking, being like, well, this is supposed to be an integer. How do I decode that 11000001 into an integer? I go, well, okay, it's 97. But if I were to tell you, no, 11000001, it's a character, you go, oh, okay, well, I know to decode that as the lowercase a. So the decoding of what that series of ones and zeros means, like how to decode it depends on what its type is. Is it a character? Is it an integer? Interesting little thing. F strings. This is probably the easiest way to get yourself some nice formatted strings. You do it by starting with a lowercase f, followed by your string, and it gives you a way to easily insert like variable values into your strings. So if I were to run this, I would see my name is John Doe, and I love CSCI 161. So it replaces name with John Doe, and course code with the value of course code. You can even this has a fancy little extra little symbols there. It's sumfloat :2f, which is a way to say, so sumfloat is 456.789, but by saying .2f, it says only give me 2 decimal places. And it does the rounding for you, which is nice. You can do special alignment, like if I wanted to print a bill, and I were to do it, I'd have, it'd be all over the place. But with F strings, you can say, no, I want it to be 8 characters long, and it's going to be justified from the... So there's ways to format it, really fancy. In this particular example, I'm using literals, but they're just stand-ins for any value. It could be a variable. Obviously, this is just scratching the surface of what you can do. Obviously, this blitz of information I just told you is not something you should ever even consider memorizing. The takeaway is, like with F strings, you know they exist, and you know that if you want to do some fancy formatting with the strings, you just go to Google and type in Python F strings. And there you go. Right? Do a quick search on Google. Python F. I even give you a link. You get to the point where, how do I do this in Python? Just look it up. right? That's like no one memorizes all of the things that you could know. Everyone just knows enough about what they need to know so they can look up everything else. So don't think of memorizing any of the things I just showed you. I'm just letting you know, here's a bunch of things you can do. Cool. So before I carry on here, I want to say that everything I'm about to say, I'm going to keep very high level. We're going to talk about objects. And we're going to hit objects hard late in the semester. But as of right now, I'm just going to scratch the surface of something because we're talking about that. We have, classically speaking, we have types that are primitive types. Integers, floats, and Booleans. They are nice, simple little pieces of information. You know, we represent them with binary. 11000001 is 97, I think it was, but also the letter A, whatever. Those are the primitive types. They're actually kind of like interchangeable because it's just a series of zeros and ones. It just depends on how you decode them. But strings are a little different because strings, like we had that issue where like, well, what if the string is more than one character long? How do we fit them? If it's 5 characters, do I need 5 seats? You know, they're a little different. Strings are what we call objects. And an object, it's just like another data type, but it's a little bit more sophisticated, and there's a little bit of extra stuff that goes with it, including something that we call methods. Now, if you look at this, this is a function. If you look at this, character is in, that's a function. Those are 2 function calls. They were print we didn't define, but we could still call the print function, and then character is in is a function we wrote, so we defined it and we called it. Those are functions. But there are things called methods that look a hell of a lot like functions, but they're a little bit different. And you've all used an important method on strings already in lab. Can anyone try to guess what it is?
Data.split.
Split. You said data, which was the variable name holding some string. And then you said dot split. That dot is where we're starting to say, like, okay, I'm calling a function that's about the information in that string variable. If you go to Colab, and I just say, like, and then I say ASD dot, and I wait a second, you will see a pop-up of a lot of things. These are all methods you could use. They're going to act just like functions, but they're being operated on that specific string. So when you split the string, you split the string you were calling split on. So I didn't have to pass a parameter to split, it just worked. So there is a function called upper that will take your string and make it all uppercase. I said function, I meant method called upper. And don't worry, I'll come back to this on Tuesday. But if you're wondering, well, why wasn't there just a function called upper that I would pass the string to? And you're right, there totally could be. There's nothing stopping someone from doing that. But if you're going to ask, well, why was it a method? Well, it was a design decision where, well, you know, this method is going to be run on specific strings, so it kind of makes sense to make that method kind of like package it with the data. You know, you could tell the data to uppercase itself. And if you're wondering, how the hell am I supposed to know when something's a method versus a function? The answer to that is, you're not. With practice, you'll get a sense of it, but again, if you ever need to think to yourself, how do I convert letters to uppercase in Python? Make string uppercase in Python, like Google will tell you. Because you're not expected to memorize that stuff. You'll go crazy if you try to. Anyways, I'll see y'all Tuesday or a bunch of you this afternoon.